All right, so almost any machine learning algorithm is going to work pretty much out of the box with numeric features. Now, features that are not numeric, we definitely always need to do some modifications. However, with numeric features, we don't necessarily. However, there are a couple of things that we need to be considering with numeric features. One of them is that some algorithms that we're going to be applying throughout this course actually have or make some assumptions regarding the distribution of the features, right? And there's two primary concerns that can be introduced because of this distribution idea. One of them is the scale or the magnitude of which the numeric values are represented in. So if we look at some of our numeric features within this Ames data, you can see that we have some that are relatively small, such as here, I think this is the lot frontage. So we have values of 21, 21, 24, 50, and so on. However, we also have the total lot area, which is much larger because lot frontage is just the measurement of basically the beginning of your lot, which is not going to be that big. But when you take the lot area, you're taking the entire area that house resides on. And this can be much bigger naturally. So you can see we have down here, the ninth observation, we have a lot frontage of about 98 feet, where we have lot area is basically 13,260 squared feet. So you can see much larger differences. And we see that across many of the other features, right? Now, another issue that we can run into is the shape of our numeric features. For example, we often have a lot of numeric features that are skewed one way or the other. For example, here is the total ground living area. That's the total square footage of a home. You can see that we have a lot of the homes down here in that 1,000 to 2,000 square feet range, but it's definitely skewed right where we have kind of a long tail, where we have many homes that are 3,000 square feet all the way up to 5,000 and more square feet, right? And that causes this skewed distribution. And this skewness can cause problems in certain algorithms. And also, if we were to look at basically the relationship between ground living area and sale price down here, you can see that for the much larger area, for the much larger homes, that is where the errors or our residuals become much larger, right? So this is also related to this kind of skewed issue. So both of these concerns are things that we should be thinking about. So let's talk about the scale of numeric values, right? We should always be considering what's the scale of our individual features, and are they on a common scale or are they on a scale that is much different than one another, right? And so what we often want to do for many algorithms is to actually get all our features on the same scale. So if we take a look down here in this image, you can see that we have three features, x1, x2, and x3. And these are on somewhat different scales. You have x3 is, down here between 100 and 200 units, where x1 and x2 are down here closer to 0. So in certain algorithms, when we have features like this that are much different in the scale or the magnitude of their values, then those values that are much larger sometimes can bias or dominate the algorithm that we are applying. And so we'd want to do what's called standardizing these to be on the same measurement. And so you could see if we were to standardize these variables over here on the left, right, they end up looking like this on the right, where they all have pretty much a mean of 0 and a standard deviation equal to 1. Right? So now these are on a comparable value system where one value is not going to trump the other ones depending on the algorithm that we apply. So whether or not we need to do this normalization process kind of depends on what model that we're actually going to be using. For example, linear regression models, logistic regression, regularized regression, which we're going to be talking about in the coming weeks, and also certain algorithms such as k-nearest neighbor or neural networks, these all benefit from making sure our features are on the same scale. Now, some algorithms just really don't care. Basically, the tree-based algorithms, such as decision trees, random forest, and gradient boosted machines, they do not care what the difference is in the magnitude of the values. However, those algorithms that don't really care about it, they do not suffer if we were to actually standardize or normalize our values. So bottom line, when in doubt, it always makes sense to go ahead and standardize our values so that they're all on the same magnitude or scale. So how do we actually apply this? Well, we can apply a step normalize. So this is a function that is provided by the recipe package. And what we do is we actually take the recipe that we built earlier on, and we're going to add on to that with this step, the step in our recipe that's going to normalize certain features of interest. So here we could say, hey, look, I want to go ahead and normalize the GR live area, that's the total square footage area of a home, and year built. So this is going to go ahead and standardize these two features to make sure that they have a mean 0 and a standard deviation equal to 1. Now, what we could also do is say, hey, look, I want to normalize, or excuse me, I want to standardize all of the numeric features. So all the numeric features in my data are on the same magnitude. Now, rather than having to list out all of the features, there are some helper functions that allow us to identify certain features of interest. So one of these is this all numeric predictors. So I can include this within my recipe step here, and it's going to apply this function, which is going to standardize our features, and it's going to apply that to all numeric predictors. All right. So this is very similar to some of the helper functions we saw several weeks ago when we were working with dplyr in the select function, except these are specific to identifying what type of variables we want to work with. And there's a few different selector functions, such as all numeric predictors. We have all nominal predictors, so this would be all categorical predictors. We can use all predictors, and there's several other ones. We can even include some of those select helper functions we saw earlier, starts with, ends with, contains, directly in these recipe steps. Now, one thing to realize is this code that we apply over here, this is not actually making any transformations on our predictors yet. This is literally creating a recipe, or think about it's creating a blueprint that will be applied later on. So it's just containing logic that we want to bring together as far as how we want feature engineering to be applied down the road, but it doesn't actually apply it yet.